Okay. Recording is in progress. Very good. So one thing that I would like to know, and maybe before leaving class, write it down in the chat. I would like to understand, because it's the first year that we do it in this way. I mean, it's the first year that I'm teaching this class. So I don't have previous records of that, but Mike has been doing it for a long time and so on. And we changed it a bit with respect to how Mike was doing it. I would like to know from you, if you could send it in the chat, how do you feel about how we structured the course? So with the asynchronous lectures, the videos on YouTube that you can watch whenever you want, and you can watch even multiple times if you are not familiar with all the tutorials, with the solutions, and then the fact that we have these Zoom online lectures where we do some some review of the slides. And then we also are going to do some problems. Today, you'll see we're going to do some problems. It's true that so far, because we lost kind of one lecture per week of our Zoom lectures. One, because it was to present the course and to discuss about the syllabus and how, because this course is complicated in the sense that it's very structured with the recitations, with lots of things to do. So we spent all the first class describing that. Then there was a holiday. Then another time, I do not recall. So we didn't have weeks where we had entirely two lectures to discuss about the course material. So you will see that this week we are going to do more problems in class. And so I think that this is good to use a bit of our time to go through the problems. And then also the fact that we have the chat with our wonderful TAs that are replying right away to your questions. And then the fact that we also record the Zoom synchronous lectures, so that if you cannot attend for whatever reason, you have the possibility to watch them offline later. So I would like to understand from you if you like this format and how we could improve it for the future. You know, it's always good to have inputs, and there is always a space for improvement. So please leave a message at the end of this classroom so that we can improve. Okay, now going to the topic of today. So we said we are going to...
Sorry, Veronica, I'm sorry. Sorry, not to spend more time on logistics, but Julia, I wanted to say something.
Yeah, I just wanted to mention that we as LAs made a survey, and so you'll have an opportunity when that survey goes out to expand upon your feelings about the course and any suggestions you might have on how to improve it. So there will be another opportunity for you to give feedback.
Very good.
Right, it'll be a Google form, right? Great.
Yes, great. And okay, so today let's review lecture 8. Before reviewing lecture 8, let's do this review quiz. So this review quiz is: starting at the edge of a tall building, you throw a basketball directly upward with initial velocity v0. It raises straight up, then falls straight back down, and you catch it at exactly the same position where you throw it. Okay, so it says explicitly ignore air resistance. Okay, so because it says ignore air resistance, you know that we have an acceleration which is constant, right? And it's gravity. So this acceleration is what is the ball acceleration while it is rising? So we know that it's 9.8 meters per second square. So B for sure is a wrong answer. We know that there is an acceleration. Now, is it upward or downward? So it doesn't say anything about the reference system, but when it doesn't say anything about the reference system, we can kind of decide and that so the y-axis is increasing going up, and so is 9.8 upward the right answer? No, of course not, because in this case you have the gravity will pull up, which is not true. We know that it's pulling down, right? So the correct answer was C. Then what is the ball acceleration when it's at the highest point? So why is the highest point? We know that it starts with V naught velocity, and then our velocities, it decreases while we are going up because of the presence of the acceleration. Remember that the velocity is equal to V naught plus acceleration multiplied by the time. The acceleration is negative because it's going downward, so it's like it's minus 9.8, right? So because it's negative, V naught is going to decrease with time. So at the highest point is when the velocity is equal to 0, right? So what is the acceleration? Oh, sorry. What is the ball acceleration? Is not asking about the velocity, it's actually asking about the acceleration. What is the ball acceleration when it's at the highest point? So the velocity is 0, but it's not what it's asking. Sorry about that. The acceleration is constant. So it's still 9.8 meter per second squared downward. And this because we said we ignored the air resistance. And here is specified, but even when it's not specified, you should, so what you are going to have in the problem is what we have done. So you never saw so far anything where we have a non-constant acceleration. So essentially here, the acceleration is always constant and always going downward. So here is asking, the ball's time of ascent equals its time of descent. Is it true or is it false? We know that it's true because, so again, here, what it really, the acceleration is always constant. So it goes up, the velocity decrease, it gets to 0, and then it comes down, and with the exact same time, because from 0, then we have the velocity is equal to V naught plus AT. And again, A this time is in the same direction of the velocity. So the velocity is going to get increase again. And we are going to have that let's say cross the x-axis at the exact same time. So the time of ascent is equal to the time of descent. What is the ball's average velocity over the entire path? So this is equal to 0, right? Because as we said before, you start with a positive V naught, and essentially when you get back down to 0, you have a negative V naught. So the average velocity is V final minus V initial. So at the end of the day is equal to 0. And what is the average speed? So remember that the average speed is different from the velocity. So you have to consider the complete distance over the time. And Mike, I don't know if you wanna write.
Yeah, I can solve this one.
Here.
All right. I also want to mention for the previous one, average velocity. Remember that average velocity is equal to displacement over time.
Yes.
You don't even have to solve for the time because you know that the displacement for a round trip is 0. So if this object's making a round trip and it's ending at its starting point, you know that's automatically 0. So so that's also another way to get to that same answer, right?
Yes.
What Dr. Binney was talking about was just the symmetry of the path, right? You know that the path is everything about the ball's motion is basically symmetric on the way up as it is on the way down. So that's another way to sort of reason your way to the same answer.
Yeah.
Okay. Yeah, I can solve the very last one, question E. I'm going to need to put up a plain whiteboard because it's going to take a couple lines of algebra. Is that all right? I'll do that now.
Yes.
Okay.
I think it's good if they see it so they know.
Okay. Okay, everyone. So I would normally ask the room if someone could tell me what the formula is for average speed for an object, but there's too many of you. So I'm going to just, I'll just do it. I'll just remind you that we covered this before. The formula for average speed is total distance traveled over the whole path divided by the total time that it takes. Okay, so what we're thinking about here is we're thinking about the entire path from where the ball is launched all the way up to the top, okay, all the way back down to where it's caught right here. Sorry about the traffic noise in the background. All right, now let's just think about the motion of this ball briefly and put a couple things sort of in our toolbox. All right, first of all, what is the velocity going to be up here at the top? Let me give you a moment to think about that. All right, well, the answer is going to be 0. In fact, indeed, that is how we define the peak of the motion, right? That's how we define the peak of the arc. So right up here at the top, and I'm going to call that V sub peak, although you can call it V sub top or V sub mid or whatever you want to call it, right? You got to pick a name, right? We know that the velocity up there at the peak is going to be 0. I'm also going to be interested in finding if we call y equals 0 down here at the level where it's thrown and caught, then I'm going to be interested to find this height right here, because the total distance traveled is going to be 2 times that height, right? And then I'm also going to want to know, so that's not given, that's something that we're going to have to find. And then I'm also going to want to know what is the time it takes to get up there to the peak as well, right? So that's how I'm going to be able to figure out the numerator and the denominator to this expression here for the average speed. All right, good. Then one last thing that I want to put in my toolbox, what is the acceleration of this object of this basketball at all times, assuming that we choose the positive y direction to be upward. So I'll let you think about that for a second. Remember, this is an object that's in free fall. So at all times, the acceleration is going to be g in the downward direction. So if I choose positive y upward, then the acceleration will be negative g at all times. It's always negative g, even when the ball is rising, as well as when the ball is falling, as well as when the ball is at the peak. So because of that, we can use our equations for kinematics for constant acceleration, because the acceleration of the ball never, ever, ever changes. This is, of course, in an airless environment, right? We're assuming no air drag. All right, so these are the things that we know. We know that the velocity at the peak is 0. We know that the acceleration the entire time is negative g, and we're interested to find the height at the peak and the time it takes to get up to the peak. So let's calculate those 2 things, and then we can go back to our average speed calculation. All right, so first of all, let's get the time. You can do these in either order, doesn't matter, okay? I'm going to use equation 1 of our equations of kinematics. We know that the velocity up at the peak is 0. We already talked about that. And we know that the acceleration the entire time is negative g if we choose positive y upward. So that means the time it takes to rise from the throw over little g. Good. And notice that's half of the total time of flight. So I'm going to have to double that before I plug it into our formula over here for average speed. Now let's get the distance. Let's use our third formula of kinematics. By the way, there are multiple correct ways to proceed. So you could do the same calculations using one of our other kinematics formulas. I'm just going to choose these because I think they're fast and efficient. Now let's plug in what we know. We know that the velocity up at the peak is 0. And we know the acceleration the entire time is negative g. So that lets me calculate that the height at the peak is v naught squared over 2g. Now again, this is only half of the total distance traveled, right? That's just the height going up, right? All right, great. So now let's finally calculate what we want. The whole question was average speed. Average speed is going to be the total distance traveled divided by the total time it takes. Or if you want, you could just go half the distance traveled divided by half the time. That would also kind of work, but let's be safe. Let's be on the safe side. We'll do the entire trip. So the entire round trip is the distance is 2 times the height on the way up. And the entire time is 2 times the time it takes to get to the top. 2 times V naught squared over 2G, 2 times V naught over G, simplify, and the answer we get is 1/2 V naught. And that was the answer that was circled on the previous slide. I'll leave this up for just a second or two.
Very cool.
Notice how I started, just to review here, just notice how I started from our definition of average speed, right? That was what I started from. And then I looked at the stuff, the terms that are in that formula, and I asked myself, how can I then get those terms? Okay, I can get the time of flight from this calculation here, and I can get the distance traveled from that height calculation there. And the formulas I used were our formulas for all free fall problems. We're going to use our formulas of kinematics for constant acceleration, because we're going to assume constant acceleration of G in the downward direction.
Yeah, right. So I think that this calculation is very useful for our students. Now, because it's an example of the problem, right? So now let me share again the screen. Share. Okay.
I just glanced at the chat, and I just want to clarify, and I tried to really hit this hard in the lectures, on the video lectures. The constant little g, when you see a little g in any of our equations, you're always going to plug in a value of positive 9.8. Okay, little g, think of it like a constant, like the mass of a proton or something, right? You always, or the speed of light, you're always going to plug in a positive value, maybe I need like red, positive value for little g. This is important when we calculate our weight, the weight of an object. The weight of an object will be m times little g, right? So little g is a positive quantity. Sorry, did I say it 10 times yet? I think I just said it 5 times. Little g is a positive quantity. All right. Now, you'll notice in every equation in our textbook, the minus sign appears in front, right? Yeah. Yep. So what we often do is we say the acceleration is equal to negative little g. That's the way we write it. Negative times little g.
Yes.
Does that make sense? Okay, thank you. This is, I'm sorry, Veronica, this is like one of the most common errors. This is one of the most common errors I see. And as a result, people get the wrong sign on any term that has little g on it. And then they make an algebra error.
Yes. So always remember that is the attraction of our planet. So it's really pulling down, right?
It is, right.
Yes.
So the y component of the acceleration is often negative little g, negative 9.8. But the little g itself is always, you always stick in a positive quantity for it, just like you would speed of light, mass of a proton, things like that.
I remember my professor in Italy was making this joke when he was teaching us this thing. It was said, okay, now I take your book and I throw it out of the window and you can go upstairs to pick it up. So it's because
you go upstairs. Nice.
Yeah, and go upstairs to pick it up. And you were like, oh no. So if you make this mistake, always remind yourself that it goes down. Everything that you throw up from the window goes down, doesn't go up. And this is because of gravity. Okay, so let's move on. And let's start with vector versus scalar quantities. So scalar is a physical quantity that contains no sense of direction, while vector is a physical quantity that also requires a direction to specify it completely. So because of that, it has a magnitude that says the size or the strength. So essentially a number, 1, 10, 1,000. And then we have a direction which tells you if it's positive or negative, right? So for example, so when you already know that the vector quantity, for example, what it is the acceleration, right? Because we just said it's pointing in a specific direction. So you need this direction, but then you also have the displacement, that is a vector, the velocity, which is a vector, while, for example, the distance traveled, it doesn't matter in which direction you go. When you look with your iPhone, how many steps you have done, it doesn't really matter in which direction, it just matters what number of steps you have done. So the distance traveled, the temperature also is a scalar because it doesn't matter the direction. I mean, it is a positive or negative, but is a scalar because it's really doesn't matter the direction, doesn't have a sense of direction. And then the same is time. There is the past, yes, there is the present and the future, but it doesn't really need a direction. A direction means an X, Y, Z to understand. The same is about the energy, which is a scalar, the speed, and then the power. So let's see better about the vector. So what you do is typically you have a quantity that you want to put an error here, on the top of it. And this is a full vector. So the full vector, instead, if you have something like that, I mean, boldface, italicized, this is a bit confusing. And it's true in the books, sometimes you find something like this, but normally the way you want to write it is really like this. So if you write a vector like this, there is no confusion. We know that you mean a vector. While if you write the number or the symbol within these bars, then we know that is the magnitude only. And because it's the magnitude only, is always positive, because it's like we remove the direction from the information. While theta is going to be an angle that is going to define the direction, so the trigonometric direction. And positive is measured from the x-axis, and negative is measured from the, how do you pronunciate this, Mike? CCW, I don't know.
Counterclockwise or clockwise.
Counterclockwise or clockwise, sorry. Sorry for my English.
That's right. If you're British, they say anti-clockwise, but you know, yes. That's if you want to sound pretentious.
No. And then something that is also exists, which is compass bearing, and we call it this with phi. And this is used by sailors, hikers, pilot, and so on. They start to measure from the north direction through the east. So we will see later, is a bit different from the trigonometric one, right? The trigonometric one, you essentially start from east. And then if I go to the next page, you will understand better when we discuss about this. So I don't want to lose time here. So then, for each vector, you have the components. Components depends if we have a 3 axis, is going to be ax, a y, a z, or 2 axis, then you are going to have ax and a y, or and so on. So a vector will lie a Cartesian point, x, y, and z, and this is also the way that we can write the components. So for example, in the notation, if you have a equal to, between the brackets, you put ax, comma, ay, we know that those are the components of the vector in 2 dimensions, or in 3 dimensions if we put also z, okay? Another way that we can indicate it is with I, j, and k, which are essentially the same thing that you would say x, y, and z. But, you know, sometimes we have multiple ways to express the same concept, the exact same thing. Or this is another way that you can write it, with this x with this sort of hat on the top of it. And imagine that every time when you see ax, a y, a z, this is a number. This is going to be a number, right? So for example, let's see right away an example because it's easier. So here we have V naught, which is a velocity, is 35 meters per second at 40 degrees above the horizontal. So this is the horizontal, our trigonometric way of writing these things. So 40 degrees, here is the direction, and then V naught, we indicated with an arrow that has its origin in the origin, and then you have the arrow here, okay? And this is your V naught. Close to it, you want to put V naught with the arrow on the top of it, because you want to make sure that whoever is reading your homework, your elaborate, your work understands that you know that this is a vector, okay? So always don't put only V naught, put V naught with the arrow on the top of it. Then if we consider, this is a way to define it, right? You exactly know the magnitude of this vector and the direction of this vector. So These are the two things that you need to identify univocally vector. But also we said you can also describe it and define it if instead we provide the components. So here we have the components along X, the components along Y, okay? In this case, we also indicated with this. So we can also indicate it as a plus, and here put I and J, and here put X and Y. This is exactly the same way of writing this one. Sometimes you might have a three-dimensional vector, and you might have a 0, for example, in the Y component, and instead something different from 0 in the Z component. So it's important that you really, in case that 0 is in the middle, it's important that you put it. If it's like this, it's already provided the fact that we don't have any Z components, right? So here, look, we have.
That's right. We'll pretty much only have 1 and 2D problems in this Phys 151. That's right.
Yeah. So, which is makes your life way, way simpler. So here, what you have instead, we know the X component. So what you do, you just draw a vector. You just draw a vector with the origin in 0, going is positive, right? Because it's plus 26.8. So you need to go in the same direction of the plus X. If it would have been negative, you would have gone in the opposite direction, right? So here you just make as a drawing your first vector in the X component, then you draw the Y component, which is also positive, so it's going in the same direction of plus Y. And after that, you have to do these dot lines, and see where they cross each other. So one parallel to the X-axis and another one parallel to the Y-axis. And then you do this, you draw this diagonal, and you see that this diagonal here is exactly the same one of this one. So this is going to be your vector V0, again with the error on the top of it, which is indicated is a vector. At this time, you find V0 using the component along X and Y. And this you can call it V0X, and this you can call it V0Y. V0X is the projection of V0 onto the X-axis, while V0Y is the projection of V0 onto the Y-axis. Okay, so here we have another example, full vector, which is 2.3 meter at 250. So when no information is provided, then you assume the trigonometric direction. So again, here you are going to do 2.3 meter is the magnitude, and then the trigonometric direction is going to be 250. Compass bearing, we defined it before. The compass bearing is the one that is starting from the north, because normally you have the compass that indicate the north, right? And so, and then you move from that going through east. So if we look at here, what we have is that the green indicate the trigonometric direction. So we simply say 2.3 meter is the length, is the dimension of the magnitude of this vector, and then the direction is 250 degrees. So 90, 180, and I'm going to 250, which is right a bit less than here, right, which will be 270. So something here, okay, this is the trigonometric one. And then instead with this other color, violet, you have instead the trigonometric direction, the compass bearing direction.
Compass bearing, yeah.
Yes, which is 200. So 200, you're going to have 90, you see, going towards plus X, towards the east side, 90, 180, and then it's 200. So you just go here. Okay, so I hope it's more clear now. Here, for example, we want to see another way So with the components this time, because it's going to be in this quadrant, you know that it's going to be negative x, right? Because it's in the negative side of the x axis, and negative y, because it's in the negative side of the y axis. And then the components are minus 0.79 meter and minus 2.16 meter going down. Again, you do your dot lines here, and wherever they encounter, this is the point where you want to put your arrow. And so you start from the origin and you go up to this point, and this is going to be your vector. So maybe some of you already know these things, but it's important that we clarify all those, because you are going to use vector quite a lot. So it's good that it's clear to you. Then, so any vector forms a right triangle with its x and y components, right? We see that here is 90 degree, here is 90 degree. So to keep things consistent, I will use only the trigonometry direction angle theta, and never any other direction angles. So here, if we have, for example, in this case, if I have the magnitude and I have the direction, but for the problem is useful for me to find the components, or the problem is asking me the components, how do I do that? So AX is equal to A cosinus of theta. Indeed, here is A, and we know from trigonometry, this is theta, right? The direction from the X. And we know from trigonometry that this part here, from 0 up to that, is called AX, and AX is equal to A cos theta. Very good. Then AY, which is the component of A along the y-axis, is instead A sin theta. It's good if you memorize those, or you really make them clear when you do your midterm, and you want to have those in front of you so you can use them if necessary. Or, so this is in the case you have magnitude and direction and you need the components along x and y. If instead you have the components and you need the magnitude and the direction, then you have to do another thing. A is equal to the square root of ax to the square plus ay to the square. So you see that here, doesn't matter if negative or positive, you're going to get a positive number. Here you have the square root, and you know that A is going to be a positive number, because what it really defines the direction of your, so the magnitude is going to be positive, right? What is going to define the direction of your vector instead is this one. So you're going to have the arctangent of what? Of the component along y divided the component along x. So for our, here is an important thing. Every inverse trigonometric function has two solutions within 0 and 360 degrees. But your calculator will only show you one. So for arctangent, you need to add plus or minus 180 to find the second solution. So you first need to identify the quadrant for your answer. So you know AX and AY here are both positive, right? So you know that this theta is going to be in this quadrant because AX and AY are all positive. But if A will be in the direction of the previous one, this one, for example, you know that it needs to be an angle, right, that goes into this quadrant. Okay, so in this case, identify the quadrant for the answer and then keep the solution in the desired quadrant and discard the other solution. It makes sense, right? So that's why it's very important for you always to sketch your vector. Doesn't need to be a super nice sketch. We are not here at the art department, so this doesn't really matter, but do a sketch when you do your things. So I'm not going to cover the tutorials because these are already covered in in the asynchronous lecture by Mike, so there's no point for me to redo the exact same problems. So I found other problems that I want to show you. So let's do a problem about free fall. So we have a ball that is thrown upward with an initial velocity of 30 meters per second. If its acceleration is 10 meters per second squared downward, how long does it take to reach its highest point? And what is the distance to the highest point? So it's similar to what before Mike was doing. So we start, what we know is we can decide, so plus y to be going up. We can start that we throw our ball from 0. So we are going to say that y naught is equal to 0, is our initial position of the ball. Then we know v naught that is going up, right? So it's positive, it's going up in the same direction of the y-axis plus y-axis. So is 30 meters per second. Then we know that the acceleration this time is 10 meters per second square. I don't know why the problem decided to make, let's say, the calculation simpler, is simplified to 10, but if it's not specified a different number, you always need to put 9.8 or 9.80 meters per second square. So, and we know that the acceleration is negative, is going downward, okay? And then we want to, what else do we know? So we want to know how long does it take? So the time where it gets to the highest point. What do we know about the highest point? The highest point, we know that the velocity is equal to 0. That's the reason why it doesn't keep going up and up, right? If the velocity will be different from 0, we'll keep going up. But because at some point the velocity is 0, it's stuck there. And then because there is gravity and the acceleration, it makes the object fell down, correct? So we also know that V up is equal to 0. So what we can use? So we can use, for example, this equation, V is equal to V naught plus AT to find the time. So the time is equal to V minus V naught divided by A. V, final velocity at the highest point, is 0. So 0 minus V naught divided by minus G. Minus and minus goes away. So the time is 30 divided by 10, 30 meter per second divided by 10 meter per second square. So if we do all the, if we remove all the extra things, we come out with 3 seconds. Does it make sense to you? Am I going too fast? I hope I'm not going too fast.
I think that makes sense. Yep. Right. Okay. So this gives you the time it takes to get up to the peak, right?
Yes. Yep. Then is asking how long does it take and what is the distance to the highest point? So the distance to the highest points is y minus y naught is equal to v naught t plus 1/2 AT squared. So we defined that y naught is equal to 0. So here y is equal to what? V naught 30 meters per second, t we know that is 3 seconds, plus 1/2 a, which we know that is minus 10 meters per second square, t to the square, which is again 3 seconds. We do all the calculations and we find 90 meters minus 45 meters, which is equal to 45 meters. So we know that here y is going to be 45 meters. Then he's asking, what is the total time that the ball is in the air? So at this point, we change the position and we have that y final minus y initial is equal to 0 because we start to 0 and then the ball comes back to 0, right? because back to the ground, so to 0. So we know that y is equal to 0. So y is equal to v naught t plus 1/2 at squared. And this we just said is equal to 0. So from this equation, we can take the t. T, I just take out here a t, is equal to v naught plus 1/2 at equal to 0. And this gives you two solutions for t. So this equation is true if t is equal to 0. And indeed, this is at the beginning, right? At the beginning, we have that the time just started is equal to 0. Or the second solution, which is the one we are looking for, is v naught plus 1/2 at equal to 0, right? This expression, this whole equation can be 0 if t is equal to 0, or if the part inside the bracket is equal to 0. So this we can write t is equal to minus v naught 2 divided by a. So minus 2 v naught divided by minus g. If you do your calculation, is 2 times 30 meters per second divided by 10 meters per second square, which gives you a result of 6 seconds. Do you have questions on these things? So as you see, we always use the key is to make a good drawing that you understand the initial things, see the, for example, test point, you need to know that the velocity is equal to 0, otherwise you cannot go on, right, in the problem. So you need to find these little details that you see essentially, especially if you do a drawing. It's very, very important that you do it, you write all the things that are provided in the problem, and then you simply use the formulas that we told you to memorize because they're very important. Okay, if we are good, we can go to another example. What will, with what speed must the ball be thrown? I cannot even read what I'm writing, sorry. With what speed must the ball be thrown vertically from ground level to rise to a maximum height of 50 meters? How long will it be in the air? And then sketch graphs of y, v, and a versus time for the ball. On the first two graphs indicate the time at which 50 meters is reached. So we need to find when, with what speed, so we are looking for the speed that the ball needs to be thrown vertically from ground level to rise to a maximum height of 50 meters. So we start from 0, 50 meters, v naught is positive in this direction. We have minus g because we are going down, right? And here we need to get to 50 meters. So this is what we are looking for. So we have if we look at our usual formula, so y final minus y initial, we know that is 50 minus 0 is equal to v naught t plus 1/2 at squared. So in this case is minus 1/2 g t squared. So we need first to know the time. So we know that 0 is equal to v naught minus gt. We can use this formula because we know that at this highest point, the velocity v final is going to be equal to 0. So v final, which is equal to 0, is equal to v naught minus gt. From this, we find t, which is equal to v naught divided by g. So we can substitute now here the time because we needed the time here. So in this equation, so 50 is equal to v naught multiplied by the time, which is v naught g, minus 1/2 g t squared. So v naught g at the square. If we do all the if we remove everything that is extra here, the simplification, we find V naught squared G minus 1/2 V naught G equal to 1/2 V naught squared G. We substitute the numbers and we find V naught is equal to 31.3 meter per second. Okay, in B is asking how long it will be in the air. So we need to find the time. Again, we have T. From this equation, we find T is equal to V minus V naught divided by minus G. So we know that the velocity when it gets back to the ground is exactly equal to V naught, but is negative. V final here is going to be like V naught, but here is V naught positive, while here is V naught negative. So negative V naught minus negative V naught divided by minus G. This is what it gives you. And if you do the calculation, you find 6.4 seconds. So because of the symmetry of this type of problems, again, I want to emphasize this, V naught here, the initial velocity is going to be exactly equal to the final velocity. The only difference in these two vectors is that one goes up and another one goes down. So is the direction. One is positive and this one is going to be negative because it's going to be in the same direction, right, of the negative y-axis. So now is asking to make the sketch. The sketch, we already have done it. What we can do, we can put some times that we find. So 50 meters is here at the top. When we get to the top, we get to the top after 3.2 seconds. And then we know that we got again on the ground after 6.4 seconds. This is the displacement that is doing. While the velocity starting from a positive velocity is decreasing after 3.2 seconds. We know that the velocity is equal to 0. And then we know that it gets negative exactly at the same value that it had the initial velocity. So we calculated before 31.3 meters per second. Here at the beginning is positive, here is minus 31.3 negative. What about the acceleration? The acceleration during the entire time never changed. Gravity and our planet didn't change during the time. So here we are with minus 9.8 meters per second square. Okay, the only problem I was not able to cover is this one about the vector, but maybe 2 minutes extra you can do it. So this is A. A is defined as a 5i plus 3j. So we know that 5 is the component along x, 3 is the component along y. So here is a drawing. We know AX is here, AY is here. What is asking is the magnitude and the direction. So the magnitude A is equal to the square root of AX to the square plus AY to the square. So 5 at the square is 25 plus 9. It gives 34. The square root of 34. This is what the calculator gives. And then we know that the tangent of theta is equal to AY divided by AX. And again, if you do the calculation, you find 31. So 31 is in the first quadrant, a bit less than half of it, which will be 45 degrees, right? 31. And then you put A with the arrow, design it in this way. Okay, I think that our time is over. I wish you a wonderful, wonderful weekend. And that's pretty much it.
I want to remind everyone that Julia will have office hours right here at this Zoom address starting in 5 minutes. So one of us will stay online. And we have LAs with office hours scheduled throughout the day today, right here at the Zoom address. So you can either stay online now for help or you can come back later. Please see our schedule. Julia, if you yourself would like to take a 5-minute break before you sort of begin an hour long stretch, please go ahead and do that. And I can stay online until you return.
Okay, thanks.